So radioactivity, as we discussed already, what is radioactivity? Radioactivity is basically spontaneous and random disintegration of the nuclei, unstable nuclei. So radioactive decay here refers to, it's a process in which the unstable nucleus decay by emitting out the radiation and the particles such as alpha and beta to become a stable one. We call this as radioactivity. And when a radioactive nucleus decay, it breaks down and emits out alpha particle or a beta particle or energy to form a new atom. And the parent nuclei, like first element X change to a daughter nuclei Y, and element X is less stable, where element Y will be more stable. Then we have a background radiation. What is the meaning or concept of the background radiation? The radiation which are coming from the surrounding, not directly from the source, like other than the source which we have, the radiations which are coming from the surrounding are known as background radiation. And there are many sources of the background radiation. It can be cosmic rays, means radiation from the outer atmosphere. Different types of substances, foods also emit out these radiation. Ground also, soil, it contains different radioactive material that also emit out. We are using in a medical field, we are using different types of radiation that might contribute. Or in our atmosphere, we have a radon gas, and radon gas is also a radioactive. So radiation other than the source which are coming, we receive those radiations, we call them as a background radiation, or also refers to surrounding radiation. So radioactive radiation are present all around our environment, and the radioactive materials which are there in the environment, they are always present naturally, and they emit out radiation such as ground, bricks, buildings, rocks, and cosmic radiation, radiations from stars and the sun. So even if you're sitting in your room, you're also receiving these background radiations. Amount of background radiation may vary. Like example, if you are nearby a nuclear facility or a hospital, you will receive more radiation as compared to you're far away from these sources. But it is always there. Amount may change, may vary, but it is always there in the atmosphere. Then what happens when the element, the radioactive element disintegrate or decay? So very important term we define for this in disintegration or decay is a half-life. From the name, you can understand half-life means the time it will take to be half, the time taken by half of the radioactive sample to be stable. Example, if I have 100 grams of radioactive sample, and say time is equals to 0 seconds, start. Then what happens? This 100 gram is unstable. This 100 gram is emitting out radiation. This 100 gram is unstable. So what happened? This 100 gram will disintegrate or break down into 50 grams of a stable, and it will become 50 gram remain unstable. Like out of total 100 unstable, the time taken by half of the radioactive sample to be stable. So example, it at the beginning time was 0 second, and now example time is 10 seconds. So what is the half-life? Half-life is a time taken by half of the radioactive sample to disintegrate. So 100 become 50 stable and 50 unstable. So this time interval, what we call this time interval, we call that as a half-life. Same thing, this 50 gram, which is unstable, because the radioactive material, they tend to be stable, like they try to reach the stability by emitting out the alpha, beta, and gamma radiation. So time when out of this 50 gram, 25 gram will be stable, because half of 50 is 25, and remaining 25 gram will be unstable. Say this time interval, when it was 50, it was 10 seconds, as we already know. And here, example, 20 seconds. So what is a half-life? Half-life means time taken by half of the radioactive sample to disintegrate. So this 50 become 25 in how much duration? What is the time interval? So it started with 10 and ending at 20. So the time interval is again 10 seconds. So this 10 seconds is refers to the half-life of the sample. So half-life is refers to time taken by half of the radioactive sample to disintegrate or be stable, half stable and half unstable. So all the radioactive substances decay at the same pattern. And you can see from the graph here, what this graph shows, the red spots are showing unstable atoms, like which are radioactive. Then this is the total. So then it will become half. So example, it started with 100. 100 radioactive atoms are unstable. What is half of 100? If we, in the beginning we have 100 radioactive atoms, or you can say nuclei, which are unstable. Unstable means they tend to emit out radiation. So time when out of this 100, 50 atoms will be stable and remaining 50 will be unstable. So what we call this interval, when out of 100, 50 becomes stable and 50 become unstable. So how many example unstable are there? This is a graph for unstable nuclei and number of the half-life. So 100 atoms are there. What is the half of 100? 50. So the time when 100 radioactive atoms, unstable atom, become 50 unstable atom, that time interval or the duration of the time, what we call that as a half-life. Same thing, if it is 50, what is half of 50? Half of 50 is 25. So when 50 become 25, that time interval, that duration is also known as the half-life. So the idea of a half-life is basically time taken by half of the radioactive sample to disintegrate or decay. And when the samples start to decay, the amount of stable atoms increases and amount of unstable atoms will decrease. Like in the beginning, if we have 100 unstable atoms, after first half-life, 50 will be stable, 50 will be unstable. After another half-life, because unstable will always decay, so out of 50, 25 will be stable and remaining 25 will be unstable. So this duration is also known as half-life. So as the number of the half-lives increases, the amount of unstable nuclei decrease and amount of the total sum of stable nuclei increases. So another image you can see, like if we have 100, all 100 is there, 100% is radioactive. After half-life, 50 is radioactive, 50. Basically the black shade is representing the stable and white shade is representing unstable. In the beginning, 100% unstable. After first half-life, 50 stable, 50 unstable. After another half-life, 25 will be stable, 7.75 unstable. After another half-life, 12.5 will be unstable, remaining stable. And after 12.5, 6.25 will be stable and 93.75 will be unstable, and so on. So amount of stable particles in the sample increases and amount of unstable decreases. So the graph shows how the amount of a substance decreases rapidly at first and then more slowly, but we cannot say the last atom will decay. So that's why the graph will never reach the horizontal line. Now some questions just to make you understand how to work out the half-life. Example, the count rate. Count rate means from a detector radiation which we detect from the source. it falls from 400 to 15 3 minutes. What is the half-life? How to work out a half-life? Like example, first it is 400. Then when the time will be half-life, the 400 will become 200. Basically, amount of radiation as the radioactive samples start to decay, the amount of radiation start to decrease because it will become stable. Half will be stable and half will be unstable after the half-life time. So you can solve, like example, if you have 400 radiations in the beginning, then after the half-life, after the time when it will become half, we call half-life. So after half-life, 400 will become 200. Then after another half-life, 200 will become 100. Then after another half-life, 100 become 50. So how many times, how many half-lives are there for a 400 to change to 50? So 1, 2, and 3 half-lives are there. And they mention that the radiation takes from 400 to 50. The total time the radiation takes to change from 400 to 50, that is equals to 3 minutes. So it means there are 3 half-lives because this is 1 half-life, this is a second and third. So it means there are 3 half-lives in 3 minutes. So what is the half-life? So half-life is equals to 3 minutes divided by 3. So 3 divided by 3 means each half-life is actually 1 minute. So it will take 1 minute first to convert from 400 to 200. And then it will take another 1 minute to convert from 200 to 100. Then it will take another 1 minute to convert from 100 to 50. So the time taken by half of the radioactive sample to decay is simply refers to half-life. So when it was changing from 400 to 50, it is not having 1 half-life. Actually, it is having 3 half-lives because 3 times it will become half to reach 50. So and the duration for 3 half-lives is 3 minutes. That's why 1 half-life or each half-life equals to 1 minute. As you can see here, this solution. So the final answer solution is the final answer is shown 1 minute, but the solution, as I already discussed. Another question, like example, the half-life of the radioactive sample is 2,400 years. So means after every 2,400 years, it will become half of its original value. The activity of the sample, like the amount of radiation which it's coming out every second, is 720. How long it will take for activity to fall to 90? So what we have to do, first 720. After the half-life, the sample will become half. So half of 720, that is equals to 360. Then after another half-life, this 360, half of 360 will be 180. Then after another half-life, it will become 90. So how many half-lives must pass so that it become 90? So 1, 2, and 3 half-lives. So there should be 3 half-lives. And we know time for each half-life. They mentioned the time for the half-life is 2,400 years. So it will be 3 multiplied by 2,400 years. So this will give us the total half-life of the total time the sample will take as 2,400 times 3 equal to 7,200 years. So 7,200 years this sample will take to become half of its to become from change from 720 radiation to 90 radiations. Another question, In question 3, the half-life of the radioactive material is 24 years. So we have a radioactive material which is having a half-life of 24 years. The activity of a sample falls to a fraction of its initial value after 72 years. So we want to find after 72 years how much its activity will fall. But they did not give us any activity in the beginning, so we can take any letter to represent the activity. So example, if I say original activity is so how much we want to find, because there are 24 is a half-life, and we want to find after 72 years. So means we want to find a fraction after how many half-lives, because 24 years is equals to 1 half-life. So 72 years divided by 24. So how many half-lives will be there? There will be 3 half-lives. The number of the half-lives we want to find after 3 half-lives, what fraction of the sample will be left, or what fraction of the sample will be active. So example, if originally it is activity is A, original activity, you can represent by any value, any number. If original activity is A, so after half-life, after the half-life, what will be the activity? The activity will be A by 2. Because after every half-life, the activity decreases. Then after another half-life, what will be the activity? Half of this value, so it will be A by 4. Because we want to find after 72 years, and we know 1 half-life is equals to 24 years. So here, this will be 24 years, this will be 24 years, and another one will also be 24 years. So I can write after half-life, or I can also say after 24 years, because they mention half-life is 24 years. So if I use originally it is A, after 24 years, the sample will be, the amount of sample which will be active, that will be A by 2, because half-life is a time taken by half of the radioactive sample to disintegrate or decay. Then after another half-life, after another 24 years, what will be the amount? The amount will be A by 4, because half of what was there, because first it was A, half of A is A by 2. Then half of A by 2 is A by 4. Then after further 24 years, after another 24 years, what will happen? What will be the amount? It will be half of A by 4. What is the half of A by 4? That is A by 8. So what sample, what fraction we are left with? We are left with A by 8, or 1 by 8 of the original. And how we identify, because in the question they ask how much is there after 72 years. So 24 plus 24 plus 24. So basically this total interval will be equal to 72 years. So after 72 years, what original sample was A, after 72 years, we are left with A by 8, or 1 by 8 of the original will be active. So 1 by 8 or A by 8, we can also say. Another question related to the half-life. A radioactive sample has a half-life of 6,000 years. So means after every 6,000 years, it will become half of its original value. How much time passes before the rate of emission of a sample decrease to A by 1 by 16 of the original value? So example, first we have A, because they did not mention what is the starting radiation. So example, we assume it is A. So after the half-life, after basically 6,000 years, it will become half, so it will be A by 2. Then after another half-life, after another 6,000 years, because half-life is 6,000, so every 6,000 years, it will be half of its original value, the sample, radioactive sample. So half of A by 2 is A by 4. Then after another half-life, how much the sample will be? It will be A by 8. So this was after half-life, another half-life is after another 6,000 years. Then after another half-life, because we want to find when it will become A by 16, 1 by 16 of the original value, or A by 16 we can also say. So this one is A by 8, then it will become A by 16. So this becomes A by 16. And that is also after another half-life, we can say 6,000 years. So how many years have passed so that the activity changes from A to A by 16 or 1 by 16 of the original? So there are 4 half-lives. So what is the total time interval to change from A to A by 16? 6,000 plus 6,000 plus 6,000 plus 6,000. So total 24,000 years it will take to change half of its 1 by 16 of its original value. So as you can see, not 2,400, because this is 6,000, so it will take 24,000 years. The 10 will be there. It will take 24,000 years to be half of its 1 by 6 to 1 by 16 of its original value. Then another question from the figure, sometimes the graphs are there and you have to work out the half-life. So how to work out the half-life? Graph questions are relatively easy. You just have to use the numbers. Like the sample is 4,000 years. Like in the beginning, we have 4,000 atoms. What is half of 4,000? What will be the half of 4,000? Half of 4,000 is 2,000. So when 4,000, look, when there was 4,000, what was the time? And it is not necessary you take the starting point, you can take any point. Example, if you are taking 4,000, so when it is 4,000, the time was 0. Because that is the beginning or the start. So when it was 4,000, the time is 0. When it becomes 2,000, when it changes to 2,000, the time will become 12. So when it was 4,000, time is 0, and half of 4,000 is 2,000, time is 12. So what is the time interval? So it is basically 12 minus 0, or it is equals to 12 seconds. So the half-life, the time taken by half of the sample to disintegrate, that is equals to 12 seconds. But you can take any value. Like example, we took 4,000 and 2,000. But example, if student take 3,000, another student take the value 3,000. So at 3,000, what is the time? So at 3,000, the time it is 1, 2, 3, 4, 5. So when it is the radiations are 3,000, the time was 5. Now what is half of 3,000? Half of 3,000 is 1,500. So when it will become 1500, what is the time? We will work out like here 10, 11, 12, 13, 14. This was 10. This is 11, 12, 13, 14, 15, 16. So it is 16. So when we subtract 16 minus 5, so it is about 11 seconds. The first one was coming out about 12. This is 11. So we can basically more or less, it will be same. It won't have a much difference. So normally, because maybe the line which I drew might not be accurate or at 1500. That's why I was getting 11, but the correct answer according to the graph, it should be 12. So it's not necessary you take the first point. You can take any point and just take half. Like even you took 2000. So 2000, this is 11. And then 1000, half of 2000 is 1000. Sorry, this is 12 and 1, 2, 3, 4. So 24. So this is 12 and this one is 24. So 24 minus 12, again, we'll get 12 seconds. So as you can see, we can take any two values, which will we can easily make it half and work out the time interval. And using those values, we can find the half-life. So the first one, an isotope emitting out beta particle. So when it is emitting out beta particle, the nucleon number does not change and atomic number increases by 1. So if it is 77, it becomes 78 and this 0 and -1. We already did about alpha, beta and gamma because the neutron breaks into proton and electron. So proton number increases, but the nucleon number unchanged. In the question, the half-life of iridium is 19 hours. A sample of iridium has initial radiation of 1100. Count the radiation after 38. So 38 hour, because one half-life is 19 hours. So 38 hours means after how many half-lives? After 2 half-lives, what is the amount of radiation? So in the beginning, it is 1100. So after 19 hours, after the half-life, which is 19 hours. So this 1100 divided by 2. So that will be 550. Then after another half-life, basically in 38, after 38 hours means 2 half-lives. Because one half-life, they mentioned it is 19 hours. So 2 half-lives will be 38 hours. So after another half-life, half of 550, which is equals to 275. So and total interval 19 plus 19. So means the total interval is actually 38 hours. So after 38 hours, we'll have a radiation about 275 counts. Counts per minute is a unit for the radiation. So counts per minute or counts per second is a unit. It does not have anything to do with the half-life questions. Is it clear, this question?